Hello, my name is Jeremiah Vardman. I am a student at the University of New Hampshire and pursuing my master's degree in electrical engineering. Today, I will be talking about reducing the cost of self-adapting phased arrays. The problem is that phased arrays cost a lot. This affects everyone because antenna technology affects everyone. Think of cell phones. Almost every single person has a cell phone in our society. And if we can lower the cost of phased arrays, we lower the weight, there's more opportunity for these systems to go out in the world because the antenna industry is looking for the next big thing on the horizon to replace the classical antenna that we have. First off, steerable antennas are highly desirable. They're flexible and you can maximize efficiency because you can steer the beam pattern where you want. There are really two types of systems here that can steer. You have the mechanical and the electrical. Mechanical, most of the time, the ones we see are stationary antennas that are fixed in place and they're directed somewhere. Like in this picture, you have a transmitter that is transmitting to the receiver. Or you have electrical, which is composed of a bunch of elements that together form a wave that you can direct. I'll get into that a little bit later. As I mentioned, the mechanical systems, most of the time, the ones we see are fixed in motion. You have your cell phone antennas you'll see up high in trees or whatnot, or not trees, I guess the fake trees, if you will. I see a lot of those in California. You've got dish antennas, and then you also have military applications. There are a myriad of those as well. Those are, for the most part, fixed antennas. They can be moved manually, but other than that, they don't move. You do have some that rotate on their own. They use mechanical systems that have motors, gears, and actuators, and the like. And they're pretty fancy, but they get pretty large. Like here's one that's quite large, and then here's an even larger one. These are gigantic systems. They can get extremely large in mechanical systems. So they have a bunch of moving parts. They require lots of maintenance. They have wear and tear, and eventually they'll get old and fail. Mechanical systems are amazing, and I respect them. I'm sure many of us can respect a well-oiled machine, quite literally. But they do have their downsides. Eventually, they fail quite magnificently sometimes. And the flexibility isn't quite there as far as steering goes. For example, the antenna on the left here is an electronically steered antenna, and it can change direction instantly, whereas the mechanical system has to physically move itself to realign with its target. And the fixed antenna is pure out of luck at this point. Frankly, it should be pretty disappointed with itself. It's not doing much. The usability is also there for electronically steered antennas. In this example, the car's got a giant, bulky mechanical antenna on it, and it simply falls over. It's too heavy. Now, I don't know how realistic this application is, but if that car had an electronically steered antenna on its roof, most likely it wouldn't be falling over. That might be an application where someone in industry might actually want to use an electronically steered antenna for some applications. Sorry about that. To get into it, let's go into phased arrays. And they're kind of scary looking. The electromagnetics behind it, the concepts behind it can get pretty complicated pretty fast with some fun, but most people would say probably not fun math. But they have, as I've stated already, they have so many applications. What exactly is a phased array antenna? As mentioned before, it's a bunch of elements that work together, and each element has a shifter and attenuator, and together they can electronically steer the signal. The sum of the phase and amplitude all forms the signal that is steerable. You can kind of think of it like two drops in water. There's constructive and deconstructive waves, and at some points they add up, at some points they do. If you had a bunch of those droplets together, you would have something that looks more like a plane wave. That's kind of what's happening here. And the phased array systems they can transmit and receive. They have TR modules, transmit and receive modules that delineate the function that the elements are working at, be it transmitting or receiving. You can even do some fancy math and find out where exactly the incoming wave is coming from, and you can easily pull its data. The example I showed before was a linear array. It only had a few elements in it, but you can combine a bunch of those elements together to create a 2D plane of antenna elements. And this antenna can electronically steer the signal in 3D. And it doesn't need to be this form factor. You can make it into a circular, or you can even make it conformal, so it can actually conform to different shapes. Now, it would be nice to have these antennas everywhere. It would be awesome, right? But the topic always goes back to cost and how can we solve the issue? Now, the goal is to reduce the cost of phased array antenna systems so that they can gain a greater share in the markets of signal propagation, if you will. They're the next big ticket item, but they can't move forward easily unless they can be made with lower costs in mind. One area that can be improved is that of self-correcting systems. A phased array system that can self-correct is highly desirable. In an application where signal obstructions are dynamic, such as vehicle applications, the radiation pattern will need to be adjusted dynamically to provide the user with the best signal gain possible. In addition, a self-correcting system should be able to compensate for array element failures. There are many small elements, tons of them. Large arrays can have numbers reaching to the thousands. And each of those elements has to have a transmit-receive module on them. So the complexity of fabrication and scalability increases the cost to get these systems out of the factory and out in use in the field, be it commercial, military, space use, or any other applications. So in order to mitigate this and reduce cost, there's a couple hypotheses. You can make a simpler self-correcting system by reducing the set of array elements needed. What I mean by that is, rather than looking at every single element, you can average the phase and amplitude from a predefined set to get an accurate description of what the system is doing. And that, in such a case, fewer components will be needed, which would reduce the fabrication costs, as well as the weight, hopefully. You can also use a probabilistic average by analyzing the radiation pattern rather than each element. If you can create a model of the system without looking at every single element, you've also reduced the computational complexity as well. The Q-sum methods, it stands for cumulative sum. It's a technique described in a 2017 paper by Chen and Tsai. It might be pronouncing that incorrectly. It's TSAI. And they described it as a way to detect element failures in a phased array. The paper builds off the techniques described in a 1989 paper by Alman and Fenn. And they described a way of looking at the array of mutual coupling between array elements. You can kind of tell by the pictures here, the elements can be mutually coupled because they're not per se electronically connected, but the signal propagates from each element, so they can all couple together that way. And doing so by looking at it, you can create a complex excitation matrix that describes the elements within the array. And they found that this gives an accurate description of the array radiation pattern. The Q-sum takes that a step further and adds some more fancy math and adds probabilistic systems to the excitation mathematics, but in doing so, it requires extra measurement circuitry on each element, in addition to even more heavy computation to reduce noise variance from the probabilistic models. As such, that increases the cost of fabrication. While it does work, and it worked accurately, I wonder, can it be made to do the same or similar without analyzing each element? Can we reduce the number of elements, and can we make it do the same thing or nearly as well? If the number of elements needed can be reduced through averaging algorithms, then a system could be made to correct itself using a smaller number of components, thereby reducing the weight and cost of fabrication. And the end result is to get the system to correct itself, right? So in this image, you can see that there's the damaged radiation pattern, which it's all over the place. It's not close to the original. But then the corrected version, you can see it actually fits the original. It's successfully done what it needed to do. And if that can be accomplished using the hypotheses described, these systems could see their use become ubiquitous throughout the world. Thank you.